All right, we're going to go ahead and begin here. Thank you everyone for joining us. This is SmartVisionLights, Machine Vision Lighting Basics. This is going to be Module 1, where we're going to discuss the aspects of bright field lighting today. We'll go on in other modules to discuss dark field, specular and direct lighting, and diffuse lighting down the road here. So I'm going to start with the basic definition. What is machine vision here? How about we call machine vision extracting useful information from digital images? We do this by creating images that have a high signal and noise ratio. And for the purposes of this definition, signal is the useful information we want, and noise is the irrelevant or confusing information. In photography, there's usually a subject. In machine vision, there's also a subject, but what we want to see is useful information varies depending on the type of inspection or what we're looking for. So when we constrain this definition to machine vision, then we want to look at signal as the useful information and the correct information for the image for the type of inspection we're doing. So here's a couple sets of images, and in both these cases, photography or machine vision, we like the left of each pair because there's useful information, and the information we can see is clear, concise, and can be extracted by our machine vision system to be used for determining choices. There's not necessarily a right or wrong. The left image, obviously, is you're more grainy, you're more noisy, which is less desirable. But in the right image, depending on what you're doing, probably we're looking for the date code in this case, then the left image is better. But if we were doing surface inspection or actually looking for wrinkles or defects, the right image might be better. So 6 things we have to get right to do this: part handling and placement, lighting selection and geometry, the optics, the sensor or right camera, using the right algorithm in your machine vision, and take the results and take action there. Information flow through the systems then by scattering light, gathering light, creating a digital image, extracting features that are useful for the type of inspection in that digital image, and making a decision about pass and fail. So today we're going to talk about lighting and selection and geometry, more specifically bright field type of geometry with the light placement. So to outline this, we're going to create kind of a scientific method for imaging. So for each application, then we're going to look at a part and determine how light will interact with its surfaces and what those surfaces are. Think about the part geometry, pass the light from the source to the camera, and choose lighting types and lighting geometry that will give us the best signal and noise ratio on the required features for the inspection. So we're not going to talk so much about interaction with surfaces, that'll come in later modules today, but it's important to note that light that hits the surface does one of 4 things. It reflects, it scatters, it absorbs, or it refracts. And today we're going to talk largely about reflection because that is key to our geometry as far as bright field and dark field. We're not going to talk about the surface properties as much. And in particular, we're going to talk about the incidence of reflection. So light reflects at equal angles as it hits a flat surface, and this is an important concept for today's bright field. So, though we're not going to talk a lot about surfaces today, we're going to talk, I want to mention here, specular versus matte. Specular means that it's nearly reflective, it's good mirrors, polished metals, liquids at low angles, all provide specular reflection. It really matters where you put the light. And again, today we're going to talk about light placement in the bright field area. So it's important that we understand the light bouncing off and equal and opposite angles as it hits that surface. The opposite of Specular is called matte. Matte are things like white paper, powders, ceramics. They produce a pure diffuse reaction, meaning the light hits it and scatters. But what I do want you to recognize, whether it's specular or matte, there is a primary angle of light, as you see here on the left in the bottom image, and even if it's hitting a matte surface, that light is still hitting, being scattered, but there's still a viewing angle of the camera and a primary angle of the light. So surfaces may vary. Multifaceted, where each little aspect, you can see the surface in this machine metal here acts like a mirror and reflects at different angles. Or we can have things like sugar or powdered coatings where you get surface and different angles of reflection. Or we can have flat surfaces that produce bright images but may have droplets or other things on the surface that are interesting to see. Amorphous surfaces then contain both aspects of specular and reflective. But again, even whether we're talking about specular, matte, or amorphous surfaces, there's always a primary light angle and a primary viewing angle. So no matter what of these surfaces we're talking about, our goal is to make images with a high signal to noise ratio. And again, signal for us is the correct content, the features we want to see in the object that we want to use for our machine vision inspection here. Noise is all other content in the image, whether it's true white noise or graininess from high gain, or whether it's just visual noise, other things in the image that we don't want to see that are distracting from the things we do want to see. Again, looking at the foil, most likely we want to see the date code here, and we don't want to see all the reflections. But in some inspections, again, maybe we do want to see those reflections and find wrinkles or holes in the aluminum foil, in which case we'd want to accent those and not the text that you see. So as we enter into concepts of lighting, then we're going to talk about bright field and dark field lighting. And today, again, we're going to focus on the bright field aspects. So bright field means, as the name implies, the part is bright. If light hits the surface, it's reflected off the surface into the camera and causes that pixels that it's hitting to become brighter. Dark field is just the opposite, and it's less intuitive, but dark field comes and the flatter surfaces reflect light away from the camera, and only edges or things with angles reflect light into the camera. So basically you get an inversion between these two. So bright field is the way our eyes typically see things in a well illuminated room, and what most people are familiar with for images. The same part then, though, depending on the lighting and the geometry, can give off two very different images, again, focusing on what we might want to see on the object. So how did we get these images? Well, bright field basically means light came from above, so the field of light is reflected into the camera. And as you can see from this illustration, the camera angle is very high. The lighting angle is very high, is very near the camera, and there are direct paths from the light into the lens of the camera, and you see light reflecting off the object directly into the camera, causing a bright field image. In the image on the right, then, the angle of light is very low, and what happens is light that hits the surface is reflected away from the camera, not directly in, and only light that hits an angle or some other surface feature can be scattered upwards towards the camera, and thus you get an inverted image. So how did we get there, and what makes a bright field image? Well, we're going to define what we call the W here. So what you're going to do is draw a line from the lens to the outside edge of your field of view, and whatever that may be. And then you're going to do the same thing on the other side. And then you're going to reflect the lines off an imaginary mirror, which we've shown as a dotted line here, and make it equal and opposite angle. This defines a W. So as we look at the W, the light must be placed within at an angle within this W to reflect from the light, hit the surface, and into the camera. We're basically doing ray tracing here. As a rule of thumb, the right size bright field light is typically twice as big as the field of view, because if we want these angles to come at a very steep angle and hit these edges but still have a chance to make a bright field light into the camera, then the light must exist out here at a wide enough angle to scatter rays in and make it to the camera. If the light is too small of diameter and close to the camera, you can't get those angles and you won't get a good bright field image. So the W defines the boundaries between bright field and dark field lighting. So anything within this W on the positive side here, looking with the camera at a steeper angle, then creates a bright field image. If we want a dark field image, we can place the light in many places, but they have to be outside this W at a lower angle where the primary rays from the light are going to strike a low surface and bounce away from the camera and not into the camera lens. I think the AIA has a definition out there, and a lot of people I hear say this, well, this angle is basically 45 degrees, and bright field is angles less than 45 degrees off the optical axis, and dark field are angles greater than 45 degrees off the optical axis. That's a general rule of thumb and okay, but this is not quite true either, though. Because if the camera has a very short working distance and or a very wide field of view, you can see this W would get if our field of view were out here, you can see this W would get very wide, and we would be able to have angles very steep out here as the field of view got wider. So as the field of view gets wider, these bright field angles get greater, and you could have angles that are still bright field much greater than 45 degrees. And as the field of view gets very wide, then the dark field angles become very shallow as you're looking out here, and you get much narrower, and they have to be much more than 45 degrees off the optical axis. Conversely, if the working distance is very long or the field of view is very relatively small, then these corner points here might be more towards the center of the image, and the bright field angles might only be this first kind of light that we're showing near the camera might work, and only any angle that's greater than that will be a dark field angle, even if it's only 30 or 40 degrees out here, because the field of view is very small. So it's important to recognize as we talk about the W and how to make the bright field and dark field angles, that there is no set rule. There is no magic, oh, a bright field angle is less than 45 and a dark field is greater than 45. It depends entirely on the field of view, the working distance, and the geometry of lighting setup. So what we want to do is follow the light here as we do it. So if we have a target here and we have a sample where we have a dark gray card and we have a piece of black paper, a bright glass or mirror with a specular surface, and a piece of white paper, then what the camera sees is going to be a function of our lighting angle and where we place that light. So in this case, the light's coming off here and striking this black object, but at what you can see a pretty low bright dark field angle. If we drew a W, this light's really on the edge of what our W would be. It's clearly striking the glass mirror and bouncing off, and it's reaching over to this white paper at an even more shallow angle. So consequently, though, what we see is dark because the glass mirror is outside of the angle due to this light and bouncing light out of the view of the camera, whereas the white paper, even though it's a longer angle, is scattering at all angles off the surface and sending light back in the paper. So we might see that white attenuated a little by the angle, but there's still angles based on the surface properties that send it back in there. What happens if we move the card to the left, though? There's now a path to the light via the camera to the camera via the mirror, which will appear pretty bright since we've now moved this glass mirror into the field of view, and there's now a direct angle between the mirror and the camera. So there are two ways that something can appear dark to the camera. One is the black paper, which is absorbing a lot of light. The other is it's not sending light to the camera, which was in the first positioning, and where there's no angle between the object, the light, the object, and reflecting into the camera. So now we want to talk about practical applications of bright field imaging. So bright field lighting, if we wanted to see dirt on the mirror, but not the mirror surface itself, we might use a bright field angle and look at what reflects off the mirror and see dark spots where there's a mirror. We also might want to see pin stamped or laser etched data matrix on a bright metal surface, and typically this or even a paper barcode are done in visible bright field lighting. So here's a number of bright field lighting, and it doesn't really matter if we get the angle right. We're going to look and see on specular surfaces or through blister packs and other things, you will see what happens with bright field lighting. So if you look on our website now and do a search, we have a new page with a parametric search, and one of the categories you can choose from the SmartVisionLights website is bright field lighting. If you do this, I've only got a sample. The bar lights come up right away, DDL series, dome lights come up, and other bright field. But the truth is a lot of the lights are bright field, so there's more than I can show you today, but I do want you to catch that you can search on bright field lighting. The other thing I want to point up is in our first search for bright field lighting, the bar lights come up right at the top. But if I do the same kind of search for dark field lighting, then things like the DFLW200 or dark field ring lights certainly come up later in the search, but right at the top of the search are the same bar lights. So we want to wait for a second. Why did the L300 bar lights come up at the top of both searches? And the answer to that is something like a bar light is very generic. The placement of the bar light determines whether it's bright field or dark field. So things like a bar light, which can be placed at any angle relative to the object you're viewing, can then be either bright field or dark field. They do not have a specific cause in there, and they can be generically used for either. Things like the dark field ring light, which emanates light in from the ring at a very shallow angle, is intended for close working distances, and to maintain that shallow angle, work only as a dark field light. So it's important to understand some lights have a stated purpose, bright field or dark field. Other lights, like bar lights, may be very generic, and even some of the panel lights and so forth may be very generic and may be used as bright field or dark field depending on the physical placement in their imaging scene. So one other question I'd pose to the group here is SmartVisionLights has a very common series of ring lights called our mini ring lights, RM140, and there's a smaller RM75. And this light works in a lot of different situations, but is this kind of ring light a bright field or a dark field ring light? The answer in that is it's not purely either. The inside surface of the ring light is actually curved, and the LEDs emit at multiple angles and hit the curved diffuser. And the end result is that you can get angles off the low edge of the diffuser, which are very low and typically dark field angles, or you can get angles from high up in the diffuser, which are very steep, and make bright field type images. Also, the placement of this light, if you look at these two angles relative to the surface you're viewing, can also affect this. So if you place this light closer, you're going to see more of a dark field effect. If you pull this light back, the yellow angles are going to become the dominant angles, and the darker orange ones are going to miss as you increase the working distance, and you'll have more of a bright field effect. So both bright field and dark field lights and create a hybrid effect. So besides generic lights like bar lights, which may be used as either, some lights are actually hybrid and have attributes of both and give you very smooth and even imaging, or you can control the working distance to get more or less of a bright field or dark field effect. So when we look at applications, bright field lights must fill the sky, if you will. You want to evenly fill all these bright field angles on your inspection. Again, typically the bright field angle is as wide as or more wider than the object you're inspecting, and that's to create illumination through the whole bright field area to get an even scattering and make a nice consistent image through the field of view. There's a number of ways to do this. You might use, this is a flat, though we call this a ring light, this is a flat ring light. There's dome lights, or there's what we call on-axis lights that have a combination of the dome and a on-axis dole light inside there. So if we look at what's going on with these lights, if I use a flat diffuse ring light, I will in fact cover a very wide area for my field of view. I will get light at all angles off the surface of my flat ring light, and I will fill in the bright field angles and get a bright field image. Similarly, the dome will do the same kind of effects, but the ray angles vary even more, or scattered even more. But one of the problems with the dome or the ring light is the fact that there's no light coming from the very center by virtue of the fact that we have to get an aperture to see the lens to see the field of view through. So this creates a problem. In a lot of cases, you use the bright field image and you have no problems with this. But in other cases, especially if the surface is highly reflective, you begin to see a dark center in the hole. You literally see your lens reflecting back out of there, and you get a bright image around and a dark hole in the center. This is where we use combination lights, or what we've called an on-axis diffuse light, which is a combination of the dome to get even scattering through the bright field angles. But in the center, where there's no light coming through the lens area, we use a coaxial light from the side, which actually provides light, hits a beam splitter. The camera sees through the beam splitter and back down on the surface, but light coming from the side is reflected off the back side of the beam splitter down into the optical field of view, and it fills in the hole. So the best way, if you have this problem, is to use a combination light where we use a coaxial light in combination with a dome, and we get the best of both worlds here and are able to fill in all angles of the light. The other way to look at this is what we call the warp W, because in some cases in machine vision, it's not always possible to have the camera perfectly vertical over the surface, or it may not be possible to have the lighting right around the camera. So it's very common to have cameras at oblique angles to the surface you're inspecting in machine vision, because that's where they fit. And often in those cases, the lighting can't be right on the camera for space or other reasons. But it's important to recognize we can then put the lighting at equal and opposite angles and create kind of this warped angle where we have an angle from the camera to the primary surface and an equal but opposite and complementary angle from the other side of the lighting into the camera. We can still create a bright field situation like this. So we again are not going to talk about dark field much today, other than to contrast the bright field imaging. But on the left, you see a wrench that's under a machine vision system, and this wrench is under bright field imaging conditions. So in this case, you can see we've done the things you see from the surface, but you notice, again, we can see the surface. If we were looking for scratches and pings on the surface, maybe we won't work with this bright field image. Maybe we need to improve it a little because we can't see the lower parts of the surface, but there are cases where you might want to see that surface. But if our goal was really to etch the edges and see the etched engravement around the letters there, then we would want to use a dark field ring light. So I just want to show you the comparison that the same object between these two, bright field and dark field, make very different images, and you must keep this in mind when you're imaging to get the right kind of image, to get the highest signal being the parts of the image you want to see over the noise. So things to remember about this is use the scientific method, three-step approach to identify correct lighting solutions. Think about how the light will interact with the object. Understand the W as we defined for you in ray tracing to determine where the light should be present and absent. Select the right light and geometry to get the maximum signal noise ratio to bring out the features you want for your inspection. Other additional attributes which we'll cover in other modules are understanding the characteristics of LED lighting sources, know how your camera responds to light at different wavelengths, and how your object responds to light at different wavelengths. Know how to use strobing to stop motion with acceptable pixel blur. Do not be afraid to use color or non-visible NIR or UV light to get your signal. And at least consider combining images gathered with different lights, color, location to get the signal. In some cases, it may not be a pure application where just one principle of lighting or one wavelength of lighting gets you the best result. And lastly, use filters when required to improve contrast or filter out ambient light. Lastly, and finally, remember, SmartVisionLights is your partner. We're here to help you win business and get it right. SmartVisionLights wants to be your go-to for the how-to in lighting, and we have industry experts, application engineers, and people like myself on staff to help you. If you have any questions or need application support, just bring it to us and we'll help you get it right. That's going to conclude my presentation portion for today. I'd like to thank everyone for attending.